Hey guys, so today we're going to start our fourth and final unit, which is environmental science. We're going to be going over everything from how weather patterns take place to climate change to different biomes. Today's lesson is about kind of the different categories that we organize Earth's systems by. So this lesson is called Spheres of the Earth. We're going to be going over the biosphere, lithosphere, atmosphere, and hydrosphere. We're going to be talking about how thermal energy is transferred both through the atmosphere as well as through the oceans, which is part of the hydrosphere. And we're going to go over how the Coriolis effect impacts both winds and ocean currents. So let's start with the biosphere. The biosphere is all of the living things on Earth and the environment that supports them. It is a relatively thin layer of Earth and Earth's atmosphere that is able to support life. And the other parts of the Earth that don't support life are not part of the biosphere. The biosphere has, I should say, three main parts: the lithosphere, the hydrosphere, and the atmosphere. The lithosphere is any of the Earth's crust that forms land where things live. It's made up of soil and rock. It can extend as deep as 100 kilometers below Earth's surface, where you can still find microbes and stuff like that. And it floats on the mantle that covers Earth's core. Obviously, no living things live in the mantle, which is why it's not part of the lithosphere or the biosphere. The hydrosphere is all of the water located on Earth, hydro meaning water. It includes the water in the oceans, lakes, ponds, even the water in the air and clouds. About 70% of the Earth is covered in water, and about 97.5% of that water is salt water. The cryosphere is also part of the hydrosphere, and it refers to any water that is frozen, so glaciers, ice caps, snow, all of that kind of stuff. The water cycle does have five main components: evaporation, transpiration, condensation, precipitation, and collection. And most of these should be familiar to you from elementary school. So evaporation is when liquid water on Earth's surface becomes atmospheric water vapor. Transpiration is essentially when water evaporates from the leaves of plants. Condensation is when water vapor in the air cools and becomes liquid. Precipitation is when that liquid that has condensed falls back to Earth. And then collection is essentially where water collects in oceans and lakes. It includes runoff, where essentially water is coming together and running across the surface of the Earth. So like after rainfall, for instance, water will kind of run across the surface until it kind of drains into a larger body of water. And then it also includes infiltration, which is the movement of water underground, essentially. Then we have the atmosphere, which is all the gases that surround Earth. It essentially acts like a protective and insulating barrier between the Earth and outer space. It extends for about 300 kilometers above Earth, and all of those gases are held to Earth by Earth's gravity. Our atmosphere is about 78% nitrogen, 21% oxygen, less than 1% argon, and then small amounts of other gases like carbon dioxide. There are four main layers of the atmosphere, and I have them listed here from closest to Earth to furthest away from Earth. The troposphere starts at sea level and goes to about 10 kilometers above sea level, and it contains 80% of all of the gases in the atmosphere. So it's where the gas molecules are most densely packed. This is the only layer with enough oxygen to support human life. It's also where all weather occurs. Then we have the stratosphere, which ranges from about 10 to 60 kilometers above sea level. It contains most of the ozone gas in the atmosphere, so this is where the ozone layer would be, and it absorbs a lot of energy from the sun's rays. The ozone layer is really important in protecting us from those damaging rays. Then we have the mesosphere, which is from 60 to 80 kilometers above sea level. This is where most meteors will burn at. And then our last layer of the atmosphere is the thermosphere, which starts at 80 kilometers above sea level and then goes to the edge of our atmosphere, which in some areas is 300 kilometers, in others is 1,000 kilometers. Our atmosphere is thicker around the middle of the planet. It's also where you have lots of X-rays and UV rays from the sun being absorbed, which makes the thermosphere really, really hot because it's absorbing a lot of high energy rays. The ozone layer contains lots of ozone, as the name suggests, which is an O3 molecule. And it protects all life on Earth from the damaging high energy solar radiation that is coming towards us from the sun. The ozone layer can be broken down by man-made chemicals like CFCs, which are named because they're made of carbon, fluorine, and chlorine. And that compound actually causes the ozone layer to break down and deplete. This, in the past, has caused large holes to form in the ozone layer, though those chemicals were banned in the late 1980s in the Montreal Protocol. And ever since then, the ozone layer has been slowly recovering. So I don't know if this would be like too far before your time or not, but the ozone layer back before I was born became really damaged because of these CFC compounds, and huge holes developed over the poles. After the banning of those compounds, the holes have been very gradually recovering, but they are recovering at a much slower rate than how long it took for them to develop. Like it said here, if the trend continues, hopefully by 2050, the holes will be fully closed, which is really important because ozone actually protects us from a lot of damaging solar radiation. When solar energy hits the atmosphere, lithosphere, and hydrosphere, some of that solar energy, which is electromagnetic energy, is converted into thermal energy or heat, and the rest will remain as electromagnetic radiation. That radiation can later on be converted into thermal energy. Some of that thermal energy then goes into the atmosphere, heating up the air. Some will go into the hydrosphere, and some will eventually dissipate back out into space. Thermal energy transfer in the atmosphere. So there's two main processes that thermal energy is transferred or moved in the atmosphere. One is conduction and the other is convection. So conduction is when air is heated by the land or water that it comes into contact with. So essentially what happens is solar radiation heats up, say, the land, and then the land will heat up the air above it. And then you have convection, which is when air circulates around the atmosphere, distributing that heat. So what will happen is that the air closest to Earth's surface heats up first because of conduction, and then convection will cause that heated air that's closest to the ground to rise because hot air is less dense, so it rises. Cooler air will fall down to take its place, and then that cool air also warms up because of its contact with the ground, and then so that cooled air will also rise. The hot air that had risen is going to cool down now that it's no longer in contact with the hot ground, and so it will start to fall, and you just have this constant cycling of the air closest to the ground getting warmed up and rising, the air that's furthest from the ground cooling and sinking back down again. Solar radiation can also be absorbed by water vapor and greenhouse gases, which can convert that radiation into thermal energy or heat. Not all areas of the Earth get the same amount of solar radiation. Places near the equator are going to receive the most solar energy, which is why those areas are warmer all the time. And then the poles are going to receive the least amount of solar radiation, just because of how the Earth is tilted on its axis. The equator is always kind of pointed directly at the sun, regardless of the time of year, whereas the poles, because of Earth's tilt on its axis, are never directly pointed at the sun. Wind patterns, as well as the difference in solar radiation between the equator and the poles, all causes air to circulate at different latitudes. The circulation of heat, because of convection, is broken up into 3 different atmospheric cells. The cells closest to the equator are called the Hadley cells. The ones closest to the poles are called the polar cells, and the ones in the middle of those are called the Ferrel cells. So this is what it would look like. So this would be the equator right here. So near the poles, both at the top and the bottom down here, would be the polar cells. The Hadley cells are on either side of the equator, and then the ones kind of in the middle of the polar and Hadley cells are the Ferrel cells. So that would be here and here. And you can also see I've talked about polar easterlies, westerlies, and trade winds here. Those are different types of prevailing winds that develop because of the atmospheric cells. I think, yeah, we're going to come back to that. Jet streams are fast-flowing narrow currents of air that occur whenever you have 2 cells meeting each other. So for instance, right between the polar and feral cells, so kind of right where this like white line is, or maybe a little bit below that, we would have a jet stream there. You'd have another jet stream around where this line is, another one there. The jet stream always divides cold and warm air. So we do have one jet stream above Canada called the polar jet stream, where the feral and polar cells meet. Essentially to the south of that, you're going to have warmer air. To the north of it, you're going to have cooler air. And it can shift in latitude. So it can kind of like go up and down based on atmospheric pressure changes. So like a high pressure zone can like push the jet stream, which is going to affect the temperature of the land beneath it. If you are north of the jet stream, you're going to be a lot cooler than if you're south of the jet stream. The jet stream does travel the same direction as the prevailing winds. So in Canada, that means from west to east. This is also why if you have ever flown across Canada, when you are going like from east to west, when you're flying against the jet stream, your flight tends to be longer than when you're going the same distance, but from west to east when you're flying with the jet stream. You can fly a lot faster when you're going the same direction as the jet stream. So again, for us here in Canada, our jet stream would be going from the west towards the east. Okay, the prevailing winds are just winds that tend to blow in a certain direction based on latitude. The Coriolis effect, which we'll talk about in a moment, is what causes the prevailing winds to blow in different directions at different latitudes. If you look on either side of the equator, the winds tend to blow from east to west. We call them the trade winds. Over Canada, where the feral cells are, the prevailing winds tend to move from west to east. We call them the westerlies. And then beneath the polar cells, the prevailing winds tend to also blow from east to west, like near the equator. We call them the polar easterlies. So you can also see that kind of roughly on this diagram here. So the trade winds would come down and blow this way. You'd kind of have this circling, and then this is the equator right here. So you'd have a east to west movement. The westerlies are the opposite. They kind of start in the west and blow towards the east, and they would circle back down like that. But over Canada, which is up here, you would have this movement of west to east, west to east. And it would be obviously the opposite of that as we move down towards like Mexico, the top of Mexico, bottom of the States. Okay, the Coriolis effect is essentially caused by the rotation of Earth on its axis. The Earth spins faster at the equator than the poles just because it has a longer distance to travel. So that is going to pull air and water near the equator along with it because it is spinning so quickly. Essentially, if you think of like a globe, and this is kind of a crappy globe, it's not labeled very well. But as the Earth is spinning, the equator has to travel a much further distance in 24 hours than just around like the North Pole. So if we look at any one spot on the North Pole, it has to move at a much slower rate to get a full circle in 24 hours. Whereas if we picked a spot near the equator, it's going to have to move much faster in order to make it the whole way around the Earth in the same amount of time because it is traveling a further distance. So that's what it's talking about there. The Earth also spins clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So the winds and currents of the ocean also spin in that direction. So I'm going to see if I can kind of like demonstrate what I'm talking about there. So this is a watermelon, but I'm going to pretend that it's the globe because I can write on it. So up here we have the northern hemisphere. The bottom we have the southern hemisphere. I've got an equator drawn around the middle. So if I am just going to start spinning this Earth, which is really heavy, but this is how Earth is going to be spinning. And if we look at the northern part of this, you can see that it's spinning clockwise. Now, without changing the direction that this is spinning, if we look in the south, you can see that it's spinning counterclockwise. And then again, not changing the direction it's spinning. In the north, we're back to clockwise. South is counterclockwise. So that's the Coriolis effect. It's essentially the spinning of Earth on its axis, affecting the ocean currents and the wind currents. So thermal energy transfer in the ocean. So water can absorb a lot of radiation and thermal energy without actually heating up. And the ocean currents can then circulate that thermal energy around the Earth because of the ocean currents. There are 4 different things that cause the ocean currents. One is the Coriolis effect, so this effect of the Earth spinning on its axis. One is temperature, one is salinity or saltiness, and the other is wind. So this is essentially our main ocean currents here. And like the prevailing winds, the Coriolis effect is going to cause ocean currents to spin clockwise in the north and counterclockwise in the south, for the most part. So if we look up here, obviously this is North America right here, and our main ocean current, as you can see, is spinning clockwise. If we go over to the other side of North America, that ocean current also spinning clockwise. So there are a couple exceptions to this, especially as you get further north, but our main ocean currents that affect our weather both spin clockwise. Then if we go down to the south, most of these currents are going to be spinning counterclockwise, like this one here, this one spinning counterclockwise, this one spinning counterclockwise. And that's all just because of the Coriolis effect, the effect of how Earth spins on its axis. But temperature also affects ocean currents. That is because warm water rises and cool water falls, which is how it also works with air, because hot water and hot air is less dense than their cooler counterparts. So water that is near the equator is going to absorb more radiation, it is going to heat up, and it is going to rise as it moves towards the poles. And then water that's near the poles is going to be much cooler, and therefore it is going to fall as it moves towards the equator. So that also cycles thermal energy away from the equator towards the poles. And then salinity, again, is how salty the water is. Salt water is more dense and therefore heavier than fresh water. So fresh water tends to rise while saltier water tends to sink. This is really impacted by the melting of glaciers near both of our poles, so the North Pole and the South Pole. All of that melting of those glaciers causes a large influx of cold, fresh water near the poles, which can alter ocean currents. And in fact, the ocean current in the North Atlantic is expected to slow down and could stop or even reverse because of the melting of those glaciers and the effect of that on the salinity, which can affect the transfer of heat all around the world. In fact, it would likely cause an ice age in Western Europe if that current reversed direction, as scientists expect it will, if the melting of our Arctic glaciers continues on at the same rate. Okay, I think that is all that we're going to go over for today. Let me know if you have any questions.